Hello and welcome to Abstract Linear Algebra, the video course that extends my other linear algebra course. And before we start, as always, I want to give a big thank you to all supporters on Steady, here on YouTube or on Patreon. You make it possible that I can create such videos about mathematics. And there you should know, as a supporter, you can download PDF versions and quizzes for all the videos. Okay, then let's immediately start with this new series by telling you about the prerequisites you need. As always, my Start Learning Mathematics course gives you a good foundation for all my other courses. This is what you need when you want to know how to work with sets and how to construct the number sets. And based on that knowledge, you can immediately go to my linear algebra course or to my real analysis course. And now it might not surprise you that watching my linear algebra course really helps understanding this abstract linear algebra course. However, you don't need the full knowledge of this concrete linear algebra course to understand our new abstract linear algebra course. But you need the core concepts from calculating in Rn and Cn to get the idea how to generalize these. Moreover, it also helps to have some knowledge of real analysis such that you can understand some abstract examples here. Okay, after this, I think I can give you a short overview what to expect in this video series here. In some sense, you can say we will generalize everything we already know from Rn and Cn. This means from now on we will work in general or abstract vector spaces. And then Rn or Cn are just some special examples for vector spaces. Moreover, in the same sense, we can also generalize matrices. So you should already know matrices are related to linear maps, and here we will define abstract general linear maps. Therefore, one important topic here is if we can still use matrices to calculate with such linear maps. And related to this is an important concept we call change of basis. Indeed, we can define the notion basis for an abstract vector space, and then the question is what happens when we change it. In fact, we already discussed it a little bit in the old course, but now we can discuss it in all generality. Also, on an abstract level, we will talk about angles and lengths. And there you might already know, in order to do that, we need the concept of a general inner product. There, we will see that with an inner product, we have much more geometry in such an abstract vector space. In fact, we need an inner product such that we can say that two objects are orthogonal to each other. And we will see that we have a lot of important applications for that. Okay, and now the last topic I want to drop here is the one about eigenvalues. There you might already know eigenvalues for matrices, and now we can translate this to general linear maps. Okay, so in summary we can say what we will do is that we generalize all the notions we already know from the concrete level. Moreover, I would say after doing that you will see why linear algebra is such a powerful tool in all parts of mathematics. And then I would say let's start with the first definition of this course. And this is not so surprising, this will be the definition of a vector space. And in order to understand this definition, just imagine what we already know from the vector spaces Rn and Cn. In fact, these are vector spaces because of two operations. First, we know that we can add two vectors. And as always, we can visualize this operation by putting the arrows together. And moreover, the second operation is that we can scale a vector. And with that, we have exactly what we want. We want to calculate with vectors, namely we want to add them and we want to scale them. So we need vector addition and scalar multiplication. And here, please don't forget, for the second operation here, we need scalars as scaling factors. And in fact, they always have to come from a so-called field. And of course, for Rn or Cn, this is not so complicated because they come either from the real number line or from the complex plane. And there you should know, both are fields, so you can calculate in them with the normal calculation rules for numbers. In particular, you know how to add numbers, you can multiply them, you have a neutral element with respect to the addition and another one with respect to the multiplication, and so on. And more details about that you find in my Start Learning Numbers series. The important fact here is just that we need ordinary numbers for the scaling factors in our vector space. Okay, but now we just want to put these two operations in the definition of a vector space. In other words, we will take a set V such that we can calculate with the elements in it as we calculate in Rn or Cn. Therefore, the first thing we want to fix here is a field f. This now could be any field, but often it's either the real number line or the complex plane again. Of course, the choice of the field definitely depends which problem you want to tackle, but for the moment it's enough to think of R or C. However, now the vector space V can be any set that is not the empty set. This is what you should immediately remember: a vector space can never be empty. Okay, and now by what we have said before, we know we need exactly two operations for this set. This simply means that we have two maps in the definition. The first one is the vector addition we usually denote with a plus sign. However, please don't forget, this is now an abstract plus sign. So definitely a different operation than the addition in R or C. So now we know the vector addition needs two inputs, namely two vectors from V. And then the output should be again a vector in V. So not so fancy, two vectors together give us a new vector. Moreover, on the other hand, we also have the scalar multiplication. And maybe not so surprising, this one we will denote with a dot. However, again, here it's an abstract multiplication sign. So here, again, we have two inputs, but the first one is now the field. Namely, we put in one scalar and one vector from V. And not so surprising, what should come out is a vector in V again. Now you should see, we immediately know examples for these operations when you look at Rn or Cn. However, from these examples we know that the two operations also fulfill some rules. Indeed, if we put them together, we see we need exactly 8 rules. In other words, if these rules are satisfied, we can call V a vector space. More precisely, we will call it an F vector space. So here, please don't forget, the corresponding field for the scalars is included in the definition. So for example, if the corresponding field is given by the real numbers, you would say we have a real vector space. And as I said before, at least in this course, real and complex vector spaces are the most important ones. Okay, but now, as you might expect, it's the time to list the 8 rules we need. Indeed, the first 4 we can already put together by just saying that V together with the vector addition is a so-called abelian group. This means we have the 3 group axioms, and in addition the operation is also commutative. More precisely, the first property of a group is associativity. This means if we take elements u, v, w from V, we can exchange the parentheses like that. Okay, moreover, you might also know the second rule is that we have a neutral element with respect to the addition. Of course, this is then what we call the zero vector in our abstract vector space. And then, with respect to this neutral element, we also find inverse elements. More precisely, it means that for each lowercase v in our vector space V, we find another vector we call minus v, such that the addition gives us the zero vector. So the requirement here is that all the inverses with respect to addition also lie in our set V. Okay, and then the last rule I already told you about, it simply means that the addition is commutative. Hence, it does not matter in which order we add up two vectors. Okay, then let's go to the next 2 rules which concern the scalar multiplication. And we can summarize them by saying that the scalar multiplication is compatible. And first, that means the scalar multiplication acts nicely when we put it together with the multiplication we already know from our field. So you should see here on the left hand side we scale the vector v 2 times, but on the right hand side we only scale it once. However, the claim here is that the result should be the same vector, which means you can multiply the scalars beforehand. So it means the scalar multiplication is compatible with the other multiplication. And moreover, the second rule here tells us that the multiplicative unit from our field is also compatible with the scalar multiplication. So if you multiply with the scalar 1, you don't change the vector v at all. Okay, and now we exactly need 2 rules more. Also these can be put together and we simply speak of distributive laws. And of course they are essential because they connect the scalar multiplication with the vector addition. So for example, here it means scaling the result of a vector addition is the same as adding the 2 scaled vectors. And on the other hand, if you first add 2 scalars in our field f, it's the same as adding the scaled vectors. So you see, here it's important to note that the 2 plus signs denote 2 different operations. However, now we have learned that the rules of the vector space claim that the 2 different operations act nicely together. Okay, very nice. Now we have everything. The result that we get here is an abstract vector space. And with these rules now, we can calculate inside this abstract vector space as we already know it from Rn and Cn. This means the visualization we have with these arrows also works in this abstract sense. This means imagining vectors given as arrows always helps to remember these operations. However, you should always keep in mind that the elements of a vector space are not arrows, we only use them for the visualization. Indeed, the elements of a vector space, so-called vectors, could be now very abstract objects. And I can already promise you, in the next video we will see such nice examples. Therefore, I really hope we meet again and have a nice day. Bye bye.